Basically, this will be a more applied, basically what we already seen in the previous presentations, but in a more applied way in Python. Okay. Then basically in this GitHub repo, we will have this hands-on classifier calibration, and we have the section for hands-on, a section for installation. I don't recommend to do the installation right now. If you don't have it, just follow the presentation as I go. Then there is a section for available packages for calibration at the end of this README, additional material, and please collaborate. If you want, if I miss something, please let us know and add it into this repository. Then let's go to the hands-on. This hands-on is divided into these 4 sections, basically visualization, how to train a calibrator. I will give some examples that you can just scroll later. And how can we compare different calibrators' performance. Then I will start with the visualization. If you click on these links, you will see static notebooks, and that could be enough. If you want to run the code in the web browser, you can follow this launch binder, and you can run the code as I go. Basically, clicking this button will start this binder. It may take a little bit of time to start, but after a while you will be able to see a screen like this and be able to run all the notebooks. Maybe you will be presented in a folder earlier to this one, but you go to notebooks and here you have a list of the notebooks. Then I will start basically with the visualizations. You click here and you will be open something like that. Then let's see in this part the visualizations and evaluation tools. We will basically start with a binary data set. Let me just run it. These are all some imports for some libraries. We will now here generate a binary data set. In this case, it will be just some blobs for 2 classes. And we can see these blobs being generated here. This is the positive class yellow and negative class the blue. And then how can we see the reliability diagram of a model, of a classifier? Then let's first select, divide first the data into a training and test set. And then now let's select a classifier. In this case, we will use a Gaussian naive Bayes from scikit-learn, and we will train it with the training data. Now that it's trained, let's see what is the scores that the classifier outputs in the feature space. Basically, it's giving high scores to this region, that is the positive yellow class, and to the region a little bit less because it's overlapping. But we can see that each of the samples corresponds to one of these lines of scores. No? Then how can we visualize this? Imagine that we map all of these scores of each of these samples to the corresponding score. In this case, we will get some of the samples, and this is just the instance index, like the instance 1, 2, 3, 4, 5. It is not meaningful, but the predicted probabilities are meaningful, are the outputs of the model of this classifier. You can see that high probabilities are given to the yellow points and the low probabilities are given to the blue points. We can actually do a histogram of them. In this case, we select 10 bins. And then here on the right, we can see the bins that are generated for the histogram. And these are also the proportions, or maybe the different classes on each of these bins. Then you can see that in the low scores from 0 to 10, 0.1 are given to basically all the negative samples. Then what can we do with this? Let's first make some bins. Basically here I do bins from in 10% of increments, and then we assign each of these samples to one of the bins, bin 7, 5, 4. And now we will compute the mean predicted scores on each of the bins. That it corresponds to this one, and notice that the last bin doesn't have any sample, and that's the reason why it shows here not a number. And now we will compute the mean of true positives in each of these bins. Basically are these ones. Then we can plot, or basically the reliability diagram shows what is this, what is the, for each of these bins, what is the mean predicted value on the bin, and what is the fraction of true positives on this bin. And on the right side, we can see actually the same histogram as before, indicating how many samples we have for each of these bins. For example, on the 0 to 0.1, we have lots of samples. But in the other regions, we don't have many samples. And on the 0.9 to 1, we don't have actually any sample. What we can see from this is that the model is overconfident on the lower range of the scores. Basically, it's giving the model, when it's giving, for example, 0.2, it should actually say 0.1 instead. Then this is showing underconfident predictions. And here on the higher scores, it is actually underconfident. Basically, when it's saying 0.8 scores, it actually has almost 100% accuracy or 100% true positives in that bin. Then now let's see another model, k-nearest neighbor on the same data, and then let's visualize both the k-nearest neighbor and the naive Bayes. It is the same reliability diagram, but now we are showing two of them, and we are using the PyCalib library function plot reliability diagram. We can see that naive Bayes is less overconfident here, and that KNN seems to be more calibrated in this region at least, and in this region. Okay, and here are the histograms of number of samples for each of the models. Then another way to visualize this reliability diagram is to show the gaps, as these are basically it's showing how uncalibrated are these models. And basically it's the same plot from this library, the PyCalib library, but it highlights what are these red gaps, that it's the bad on a calibrated model. And we can also compute the expected calibration error, that it's just what will be the expected gap given the scores that the model outputs. Let's go now to a multi-class problem. Here we will generate another data set. This is well, 7 features and 3 classes in this case. We will show 3 classes because we can visualize more things than with multiple or more than 3 classes. Yeah, okay. This is just a plot of each feature against each other feature. And basically now it's difficult to show the reliability diagram directly from a multi-class problem. Here what we do is to show one reliability diagram per class, meaning that on the first plot, let me just print it again. On the first plot, we have the first class as if it was the only positive, only the positive one. The second one has the second class as if it was the positive, and the rest as if it was the negative. And the third class as well. Then we can see that some of the classes are better calibrated than others. For example, the last class on the lower range, it is really good calibrated, while in other classes, the models are not that good, well calibrated. We can do the same. These are, again, the gaps, but in this case are the confidence, meaning that it's only looking at the most confident prediction per instance. What it means is that well, we have already seen that, but for each instance, it looks only at the highest score output by the model, and this is assumed to be the one that is used. And if it is correct, then it will be a true positive. If it's not correct, it will be a false positive. We can also compute the confidence C, as mentioned earlier. And the confident MCE, that is basically the biggest gap of all of them. What you can do as well is, as I showed before with the reliability diagrams per class, we can show the reliability diagrams per class with the corresponding gaps. We can see that, as I mentioned, the last class is really good calibrated at the beginning. This, by the way, is only for the naive Bayes model. And we can here compute class-wise ECE as well. There is still class-wide MCE and some statistical test ECE that we have, but I still didn't add them into this tutorial. Then what are the calibration maps? This has been covered earlier in the previous slides, but let's go again. We load the binary dataset again, and now we need a calibrator. In this case, we will use an isotonic calibration, and we will make a calibrated model with a Gaussian naive Bayes and an isotonic calibration. And we will train both of them on the same dataset. Then let's look at the reliability diagram of the isotonic model. Sorry, the calibration map. Sorry, the calibration map is showing what is the function that the isotonic is applying to the scores of the model, and basically this is somehow the correction that it's applying to the dataset, to the scores of the model, and we can see now how basically the naive Bayes looks like. That is the blue line on the reliability diagram, and how the isotonic after isotonic calibration is applied, how it looks. It's actually pretty good calibrated in that case. And we can see that now the isotonic, after isotonic is applied, the model is able to output high probabilities as well. I mean higher than 0.9 probabilities. Then what happens with ternary calibration maps? This is a little bit more complicated. I think, well, How has already mentioned these calibration maps, but what we are trying to do is just to show a map between scores and the output scores of the calibrator. In the case of three-dimensional calibrators, this is still somehow possible. Basically, the input and the output in the 3D scores are 2D, belong to a 2D simplex space, and then we can see the input space as the beginning of an arrow in a two-dimensional space, and the output predictions or the output scores of the calibrator as the end of the arrow in a two-dimensional space again. This is only showing part of the calibration map, but this can give us some insights about which regions of the space have been modified and towards which of the classes, being class 1 here, class 2 here, and class 3 here. And after that, we can actually color the arrows by the predicted class at the end of the calibrator. And basically, this is the same plot as earlier, but each of the arrows is colored by the final prediction of the final class predicted by the model, by the calibrator. Another way to visualize this calibration is by showing 3 calibration maps. This is only showing part of the calibration map again, but it's showing the full input space of the full scores, input scores, and only one of the output scores. On the left for the first class, middle for the second class, and right for the third class. And notice also that we can do some cross sections on this calibration map. And these cross sections, let me show you in a moment. With this code, we can select a number of cross sections and visualize these cross sections underneath. These cross sections will be really similar to the calibration map for one class, for binary problems, basically. And this can give you some insight of the type of calibration that your calibrator is able to perform. Following, we have just the same plot, the same plots that I showed, but just one next to each other. It's just the same, but one next to each other. Let's go to the training part. How do we train a calibrator? Okay, then let's start now. We will start. I think I will not run the code. I will just scroll because time, it will be a problem for time, but you can run it with different settings if you want. In this case, we will load the same data set as before, just some blobs of data per class. And then training a classifier, in this case a Gaussian naive Bayes, but feel free to train a logistic, a nearest neighbor, some multi-layer perception, or an SVM. We will see later examples of each of this as well. Then here we just fit the model, and we obtain the scores output by this classifier, in this case Gaussian naive Bayes. These are the score, well, the reliability diagrams again. And how do we train a calibrator? Basically, we get any calibrator that is just a function that it's able to map some scores to proper probability adjusted scores. And in this case, we will use a Dirichlet calibrator. And now we will obtain the predicted probabilities of the original classifier, and we will fit the calibrator with these scores and the true classes. Now, after that, we can see here the reliability diagram of both the calibrator, the Gaussian naive Bayes, and the calibrator on orange. And we can see how the calibrator is able to do a better job on predicting proper probabilities. We are still using the same. Training set as it was used for the original classifier, meaning that no data is added into this in order to achieve better calibrated models. In the case of the last class, it seems that it's difficult to fit it still with the calibrator, maybe because there is not enough information from the scores output of the model, original model. But on the higher range, it seems to do a better job. Here we can see the some of the expected calibration error, how the calibrator improves on that, confidence ECE, and class-wise ECE, just showing that the calibrator is actually improving on how calibrated it is. Then there are other ways we can train that. I just show step by step how we can do that ourselves. You don't need any library to do that. You just train a classifier, obtain the scores, and train now any arbitrary calibrator or a function that maps scores to proper probabilities. And here we will show some examples. This is, for example, with some libraries, sorry. This is a function from scikit-learn, a calibrated classifier cross-validation. And what this does, basically, you give any arbitrary classifier and you select or isotonic or sigmoid in this case, and a number of cross-validation faults that you want to use. What it will do is, for example, selecting 2, it will train 2 calibrators on the different faults, and then the final outputs of the calibrator will be average over these 2 calibrators. And this is done internally by scikit-learn. Then you only need to call the calibrated classifier CV, the fit function with the training set, and it will automatically train the classifier and the calibrator. The classifier can be pre-trained or can be trained here. I don't remember if by default it trains, but there was a flag here in this function indicating that you want to train or you don't want to train it. And here we can see again what isotonic is achieving, the orange lines on the reliability diagram. Here we can see again some of the metrics that we shown, and we see that the calibrator improves the expected error Then in the PyCalib library, we started implementing the calibrated classifier CV, again, similar to the scikit-learn one, but it accepts, instead of a string indicating which model you want to use, like sigmoid or isotonic, it accepts any instance of a calibrator. But it's still work in progress. We had to reformat the code, and it's currently not working, but we are working on it now. And another way is in the PyCalib library that we are developing, we have this calibrated model class. This calibrated model class is really similar to the previous one. It just accepts any classifier, and as a method, any calibrator, and it will be trained directly. These both will be trained. Then this calibrator needs to be compliant with scikit-learn's probabilistic classifiers, meaning that they have a predict probability output, and that will be it. You just train, and you will get calibrated probabilities out of it. What happens with multi-class case for binary calibrators? For example, uh, imagine we have binning calibrator, a binning calibrator, but this is defined in our case only for binary. Then what we provide in this PyCalib is a one versus the rest calibrator. This is actually an adapted version of the one versus the rest classifier from scikit-learn that we are trying to improve now, but it's working currently, and you just call the same calibrated model, you give any arbitrary classifier, but now you call one versus the rest. Well, you start an instance of one versus the rest calibrator, and you give a binary calibrator in this case. And this can still generate binary, it can still generate multi-class calibrated predictions. Although this is one versus the rest, meaning that the final output is averaged over the trained calibrators, and this may not be the optimal solution. Okay, then let's see just some examples. The third example is the third notebook is 3 binary examples, and here we are not going through all of it, but we create a binary classification problem again with these two classes, and here we show the output of all these classifiers: linear regression, logistic regression, nearest neighbor, Gaussian naive Bayes, some SVMs. With the probability option to true, this means that they are already calibrated using Platt scaling and multi-layer perceptron. When we run this code, we will obtain this type of plot where on the left side we have the scores of the model, the the predictions on all the feature space. On the middle we have the density of scores for positive and negative class, and on the right we have the reliability diagram with the gaps. Then this is just to highlight or to get some intuition of what type of predictions these different models perform in a binary classification problem. And we can see that some of the models put more weight or push more samples to the boundaries of the scores, while others have them more in the middle region of the scores. For example, the decision tree, in this case, it seems to push all the scores to the boundaries, and it has some overconfidence and underconfidence on the reliability diagram. Some other classes have things in between. For example, in this naive Bayes, because of how the problem is set, the task is set, this may be the result, and it has some miscalibration, but some good examples are radial basis function SVM, which has a 88% accuracy, or the multilayer perceptron is a shallow network that obtains 89% of accuracy. They are actually pretty good calibrated in this binary problem, as you can see on the reliability diagram, and they push a lot of the scores to higher values, basically because it's quite confident that the predictions are correct. And in the following examples, we show several calibration models on top of a Gaussian naive Bayes again. And we see the same. On the first plot of all is the Gaussian naive Bayes without calibration, and the next ones are different, the output of different calibrators. Then moving to the ternary classification problems, examples. The three ternary examples, it is basically really similar to the previous one. We will generate a data set, a ternary data set in this case, the reliability diagram for some calibrators, Gaussian naive Bayes, flat scaling, width binning, and Dirichlet. Feel free to modify what calibrators are tested here and what model is tested here. I think the best thing to do is just play around and see to get some intuition about it. Here, for example, we can see what are the scores for all the training, or in this case, the test samples, just to get some intuition again on how the model is moving the points, the original feature space into this output scores. These are the calibration maps for each of the methods. Some interesting ones are, for example, the width binning, where you can see the width, the bins being generated in this simplex as these triangles, but they are average over two or some additional calibrators in this case. And this is Dirichlet, where it shows some of the functions that it may generate that are not only sigmoidal shape, but they have these more complex shapes. Now the calibration maps, again, as I showed earlier, this is for flat scaling. This is for width binning. As you can see, the bins put a lot of scores into one individual bin, as the arrows are showing. And Dirichlet that has a more complex calibration map. These are just separated. And here we have calibration, the reliability diagram gaps. We'll not spend much time here because you can run through all of it or look at it with more time. Maybe it's important to notice that if the confidence reliability diagram seems to be calibrated, it may not be calibrated for one of the classes, as you can see here from Dirichlet. On the last class, there is some miscalibration on the low scores region. And here we show the same plots that we showed before. Then I think I have only 8 minutes now. How can we compare different calibrators? Imagine we have now run a lot of methods in different data sets and with different classifiers. Here in this example, we load the results from some experiments in a pandas data frame. This pandas data frame has, well, let me just show you below here what data set was used, how many number of classes this data set had, how many samples, what is the calibration method used in this particular result, training accuracy, test accuracy, log loss that is symbolized by loss, and Brier score, what calibration was used and what classifier was used. With all of these, well, here you can see every single data set we used, all the categories, all the classifiers, and all the methods we used. Here we select an evaluation metric. In this case, Brier score, because Brier score, optimize also part of the calibration. And then first, we will do this only for one of the classifiers in this case. Let's select logistic regression of the classifier that we want to compare. And for example, here we can see what happens with when we apply isotonic, and for one data set, we have all these results. These are just random repetitions of the experiment with different faults, test faults. And the different repetitions are these Markov chain, Monte Carlo repetitions. What we do now is to compute the mean value of for each data set and each method or calibrator. For example, in this previous example, all of these values will be averaged, and we will obtain all this table that is just an estimate of what is the performance of this calibrator on this data set after apply it on top of the logistic regression. Now we will remove any data set that has at least one of the calibrators missing, and we will perform a Friedman test. The Friedman test with this data shows a p-value of 1.7 to the power of minus 10 to the power of minus 20. This indicates that there is actually a difference between the different calibrators. Now we can run a one-tailed Venn-Foreign test that will show us, because I am running out of time, I will go quick through it. It shows here the mean, the average ranking of each of the classifiers or calibrators. And here we can see the critical difference for all of the calibrators. The critical difference shows which methods cannot be considered different. Basically, you can see that Dirichlet full L2, Dirichlet OD L2, isotonic. Well, all of these first methods cannot be considered different in this case. And this is for only one of the classifiers. But we can do this for all the classifiers by combining every single classifier with every single data set, all the possible combinations. And this is what is done here. We combine every single data set and every single classifier and obtain the mean for each of these combinations. For example, Avalon and others, Avalon and Forest, and all the calibrators. And we perform exactly the same test that I mentioned before. At the end, we obtain this critical difference diagram showing which calibrators are different to which other calibrators. Then here at the end, we have a summary of the full pipeline that I mentioned here to compare all the calibrators for you to look with more time. And I think that's it. If you have any questions.
All right, thanks, Miquel. I'm sure this will help a lot of people who want to know how to apply calibration and also perform evaluation. I think Huva is still down, so I don't see any questions there, and also in the chat. But so I will. Oh, I see someone mentioning that he got some errors on Ubuntu.
Yeah. Okay, the errors. Let's if you can open issues in the GitHub here in issues. If it's possible, I think it's possible, open issues, and I will try to answer the questions, and or maybe someone can also help to answer these questions.
So if you have any further issues and other errors, also Windows has some trouble, right?
There are some libraries, at least for Dirichlet calibration, for example, like JAX, that doesn't have an implementation, I think, for Windows, and then that could be an issue. But this could be solved not using Dirichlet calibration everywhere where it is, there is a calibration done.
Yeah, so we will further think about other solutions and maybe Docker later, and anything we can address as issues on GitHub. So now we will move on to Peter's section. Oh, sorry.
Miquel, I have a question. So when Googling for PyCalLib, I found what seems to be another PyCalLib. So are there two?
Okay, I will need to check that. I think when I created it, I tried not to collide with any other library.
Okay, it doesn't really matter, but you don't need to look at it now. But
Yeah,
that
but
may be useful to
uh,
clarify.
the library that we have been developing, but it's still work in progress, is under development. It has a pip package, and it doesn't collide with any other one in that case.
Mm-hmm. Okay. All right. Thank you. So.
I think someone was mentioning, is it possible to over-calibrate, as in we can overfit a classifier as well? Yes, of course. Sorry?
Go.
Yes, of course, we can over-calibrate as well. However, usually calibrators have some type of regularization in order to avoid that. But having said that, if the calibrator is really complex, you need to be really careful with it. Then that's one of the reasons why having a validation set for the calibration as well, and doing some cross-validation there in order to choose the best hyperparameters, if the calibrator has hyperparameters, would be desirable. Another approach would be to train several calibrators instead of only one in different partitions of the training set, and this seems to reduce or regularize the strength of each of the individual calibrators. But yeah, basically a calibrator is any model that fits some scores into a classification problem. Then they have the exact same problems as any other classifier as well. Yeah.
I think a related issue related to this question is, so for example, if you do plot scaling on something that is already perfectly calibrated, and you shouldn't actually do that because it is incoherent, because plot scaling assumes scores on a real axis, not probability scores, but nevertheless people have done that. And if you apply plot scaling to perfectly calibrated scores, you will make things worse. Whereas if you were to apply beta calibration to perfectly calibrated scores, at least beta calibration has the identity calibration map and should be able to recognize that the scores are already perfectly calibrated. So a simple example of over calibration would be applying plot scaling to perfectly calibrated scores, because it will make things worse, and that could be seen as a case of over calibration.